Matrices, transformations from historical to modern applications. A presentation by Daniel Schwartz.
What is a matrix?
A matrix is a rectangular array of numbers or symbols, individually referred to as elements, which make up rows and columns. Matrix naming convention is a capital letter, typically starting at A. The order of a matrix is a set of two numbers, the number of rows by the number of columns. Common convention is to give the number of rows m by the number of rows columns n. And for some more matrix notation, we can look at a 2 by 3 matrix. That means it has two rows, as seen here, and it has three columns, column 1, 2, and 3, as seen here. If you want to refer to the specific element in a matrix, we refer to the lowercase letter representing that matrix, followed by the row, followed by the column. So if you want element of matrix A at row 2, column 3, which is 3, you refer to it as such. A23 is 3. And for our next basic operation, we have matrix addition, where you have two matrices of the same order. You add the elements in the corresponding positions to each other for the sum matrix. So for example, you have element A11 and element B11 added together into the top left position of our sum matrix A11 plus B11. And you continue this for all the elements all the way up until AMN plus BMN gets added as AMN plus BMN in the bottom right of our sum matrix. Matrix multiplication is a little trickier. We take the rows of our first matrix and the columns of our second matrix to get the order of our product matrix. We multiply the rows of our first matrix by the columns of our second matrix, and each of the elements gets summed up, the product of these sums, to be the individual elements of our product matrix, as shown. And here's a fun one. We've got the identity matrix. The identity matrix, denoted I, is the matrix whose main diagonal, which is the one going from the top left to the bottom right, consists of only ones and all other entries are 0. This plays a pivotal role in matrices and linear algebra. Matrices are known to be particularly well suited to solve systems of equations, where each column represents a unique variable and each element represents a coefficient. So for example, here we have 2x plus 5y equals 10 and 3x plus 4y equals 24. We take the coefficients of the x's and line them up in the matrix over here. And we take the coefficients of the y's and line them up in the y column right here. And then we take the constants and line them up right here in the constant column to solve statistical equations using matrix operations. For some other common matrix operations, we have the inverse matrix, which is a matrix when you multiply it by the original matrix, you get the identity matrix. You have the transposed matrix, where the transposed matrix has the columns of the first matrix as its rows, and the rows of the first matrix as its column. And then you have scalar multiple. That's where you take every element in a matrix A, multiply them by a scalar k, and you get the scalar multiple Ka. Let's look at a very short history of matrices. It's important in their development into what they became today. Around 100 BC, the Chinese text 9 chapters on the mathematical art displayed what many claim to be the first matrix. Fast forwarding 1500 years and lots of development. Finally, the modern credit for conventional matrices is often given to the Japanese mathematician Takakatsu Zeki in his 1683 work, Method of Solving the Dissimulated Problems. Finally, in 1955, a hallmark moment for matrices, Leonard Mistry's An Introduction to Linear Algebra was a turning point in matrix theory, becoming one of the most important texts to the broad spectrum of mathematical theory studied today. For hundreds of years, we've studied matrices and we understand them very well now. And that's why, in modern times, they go hand in hand with engineering. We understand them inside and out, and they can be applied extensively. Now let's look at matrix properties and computers' needs. A matrix has a set size and a set number of elements. Computers deal with specific numbers of bits at a time. Matrices have consistent locations of elements, and computers need to quickly find specific locations of data. Matrices have well-defined operations, and computers need consistent and can use matrices to make consistent, quick results. Matrices have extensive mathematical theory behind them, and computers can use that for extensive computational operations. That mathematical theory also gives us many shortcuts in our understanding of math, and that also helps us in computers with algorithms for faster computations. Matrices can represent a wide variety of data, and computers can use matrices to represent a wide variety of data. Matrices can perform massive math calculations, and computers need to perform massive math operations. It seems like matrices go hand in hand with computers. For a quick look at a modern application of matrices, let's look at image scaling. Image scaling takes kx, the scale variable for how much you want to scale in the x direction, and ky, the scale variable for how much you'd like to scale in the y direction, times the x coordinate and the y coordinate of a certain point in space. For example, you want to stretch by 2 in the x direction and divide by half in the y direction, you use this matrix. At any given point, let's say 5, 4, you get the result 2, 10, 2.
And now for some more advanced uses of matrices.
Matrices have a mind-blowing number of incredible applications. Convolution, which is involved in image processing and averaging data and all sorts of applications. It's a presentation on its own. Neural networks, which can be used in a multitude of areas, including artificial intelligence. Adjacency matrices and graphs, which can be used in social networking and various graphing situations, communication networks, 2D and 3D object representation and manipulation. Matrices can be used to directly manipulate, translate, and rotate objects in the 2D and 3D realm. We can predict the outcome of evolving systems using the matrix operation eigenvectors. We can use matrices for large-scale circuit analysis, which would take countless hours of work by hand, but in a matrix can be done in a matter of seconds. And Google's PageRank algorithm, which you probably use today. Thank you again for listening. I hope you learned something useful today and enjoyed this presentation on matrices.